Welcome to the office. We want to take a look at a new definition, which is related to our equivalence classes that are induced by a permutation, or rather, right, the equivalence classes of the equivalence relation induced by a permutation. All right, so let's see here. What I want to do is take a look at our definition. Here we are. Let sigma be a permutation of the set A. The equivalence classes in A determined by the equivalence relation described above. So that's that same equivalence relation that we talked about before. If I want to, or if we want to, let's see here, we can go back. All right, this is the equivalence relation that we're talking about. Two things are related if sigma sends A to that. Fantastic. So we have let sigma be permutation. We get the equivalence classes that are induced induced by the permutation. That's fine. And then those equivalence classes are exactly what we call the orbits of sigma. Okay, the orbits of sigma. Essentially, what you're looking at is what kind of happens with these elements. What we're going to end up with are it's sometimes drawn in. Well, we'll look at some notation for it in our next definition related to cycles. We get some nice pictures that actually make the name orbits make sense. But we're looking at how the elements kind of travel around. Yes, it's an orbit. Where does it go? So in the same fashion that we did in the last video, what we want to do is we want to find these equivalence classes. Now, I'm not worried about the notation of an equivalence class because I'm giving them a new definition. I'm just considering the set of elements. So what things are related to 1? Well, 1 goes to 4, so 1 and 4 are related. Let's see, 4 goes to 1, and well, so that's it right there. Okay. That is our first orbit. 1 goes to 4, 4 goes to 1. Next, we have 2 goes to 2. So, boom, that's it. Next, we have 3. Where does 3 go? 3 goes to 10. 10 goes to 7. 7 goes back to 3. So that's the end of that orbit. And then we have, see here, we got 1, we got 4, we got 2, we got 3, 10, and 7. So next is 5. 5 goes to 9. 9 goes to 6. 6 goes to 8. See if I can get there we are. 8 goes to 5, and that takes care of that. So we just got 5, 9, 6, and 8. Oh, yep, I can see the mark on 7 there. So that's all of it right there. Again, this is a partition. All the elements appear somewhere in there. And that's it. So we have 1, 2, 3, 4. There are 4 orbits. Okay, so we have these elements moving around from one to another. That one stays there. These elements moving around from one to another, and these elements moving around from one to another, but they never cross, right? So we have some elements doing some things, some other elements doing some things. So that's just one element going around, 2 elements swapping places, 1, 2, 3 elements swapping places here. So 3, 10, and 7, right? It just kind of keeps going around. So that's the idea of the orbit. This is also the same picture that we'll draw when we talk about cycles. So, but it gives us a nice idea and kind of a visual representation of what's going on there. Now, you might say to yourself, well, Dr. Reinhout, you haven't mentioned the S10 here, and here it's S6. It's different. The fact that we're talking about in S10 or in S6 is primarily relevant because this tells us the set that we're working with. We're working with the elements 1 through 6 here. We're working with the elements 1 through 10. That's important more so when we look at further notational developments. Sigma, we don't have to represent in this way. In fact, after our discussion on cycles, which is coming up shortly here, we will have a much more simplified representation for our permutations. And when we have that, it will no longer be necessary to write down all of the elements in the set A that are being permuted. And once you do that, you no longer know for sure what the set A is. You have to specify. Okay, so our set A is the numbers 1 through 10, which can be observed by saying that this is S10. All right. So in S6, the numbers 1 through 6, we want to find the orbits for this permutation. So 1 is related to 6, 6 is related to 3, 3 is related to 4, 4 is related to 1. So that's the end of that one. And the next one, so 1, 6, 3, 4 we got. So now it's just 2 and 5. 2 is related to 5, 5 is related to 2, and that takes care of all of the elements in the set A, okay, the numbers 1 through 6. So that's it, just 2 orbits for this particular permutation. All right, that's it for now. We're going to take this idea and we're going to refine it slightly in our next video where we talk about cycles of a permutation or a permutation that is a cycle rather. All right, so I'll see you guys back here in the office in just a little bit for another video.